对，okay. So as we start, so we know that machine learning has been ubiquitous in the world, right? It has been applied to different domains to help make our life better. For instance, autonomous driving, intelligent medical treatment, smart city, and many like safety critical important areas like malware classification, autonomous driving, etc. So, but although like this fantastic machine learning and powerful learning AI algorithms have helped us a lot to make our life better and convenient, still we see many real world examples that even such powerful machine learning techniques still bring us a lot of like security and privacy concerns. For instance, in 2016, this is one of the favorite example I like to present because it happens in real world. And it happens like in 2016, the White House Associated Press Twitter account was hacked via phishing emails, spreading the rumor that the White House has been attacked, such that the autonomous trading bot dumped a large amount of stocks within seconds, which swept about $136 billion within seconds. And this really happens in real world. And we all know this is so-called like the fake news detection, etc. So in such a way, people usually ask like, is it too early for us to like worry about security and privacy problems of machine learning? And from this example, I believe that you will understand this is not too early and something already happens, and we definitely need to make sure we can take these types of threats into account before we can largely deploy or apply the machine learning techniques to different applications. And similarly, in the Australia airport, the biometric recognition systems have been developed for safety screening, which has raised a lot of privacy concerns in terms of like database leakage, data validation, etc. So we can see that although we are very lucky to live in a very convenient and good environment, that we have all the scalable and structured machine learning frameworks for us to develop our algorithms easily and test our models and analyze our data. But still, we are living in an adversarial environment. So a typical machine learner still have a very hard life, right, to develop the so-called trustworthy or secure machine learning platforms or models. Therefore, I believe that's why we gather together today to understand what's the potential adversarial strategies and environment, and therefore try to develop or come up with good technologies and learning algorithms to secure our model and learning process. And overall, in our lab, our goal is to design the robust, private, and explainable machine learning paradigms for real-world applications, and take a very high-level, quick overview of the things we do, and I will pick some to discuss in this talk today. So first, look at this simple pipeline. We can view this end-to-end machine learning pipeline from the input data to pre-processing and model optimization, post-processing to the final prediction or decision-making, right? And along this simple pipeline, we can see there are many things can happen. For example, different adversarial attacks, exploration, and such attack can happen during both training and testing time. And considering these types of different attacks, we can develop different robust and certifiably robust machine learning algorithms, leveraging like robust feature analysis and post-processing, like say game theoretical analysis, or leveraging additional information to further enhance the robustness of machine learning models. And of course, we hope to understand our data and understand what the black box, machine learning models are doing. So therefore, we are also focusing on different machine learning explanation, including other types of functionalities like fairness, toxicity in language models, etc., based on like data analysis. Here, one unique thing or unique project we're doing before is Shapley value to evaluate the importance or give valuations for the data for data market area now. And I will briefly mention that in this talk as well. And in the end, we of course care a lot about privacy. And similarly with the security perspective, we also explore different types of privacy attacks and privacy preserving machine learning models, etc., etc. So from this big picture, and maybe you can get some overview about trustworthy machine learning under this machine learning pipeline. But indeed, there are like hundreds and thousands of work in this area, which is, I would say, very hot area. Then we still want to ask one question, right? Since there are so many questions we want to explore here, if we only allowed to be asked one question about trustworthy machine learning and what it is and what's the core component or core questions we are trying to address here, what's that, right? So here, from my personal understanding or personal view, I would say that basically every component in trustworthy machine learning is trying to close this trustworthiness gap between different distribution drifting, either between training, testing, or distribution inference, etc., etc. We will illustrate that a little bit later. But here, I would say these slides may be the most important slides. So if you want to have some takeaway message, I think this one I would suggest would be the most important one. So overall, we want to close this trustworthiness gap from the data distribution perspective, right? We know that in traditional machine learning, we always assume the training and testing data are drawn from similar or even the same distribution, right? Therefore, we can train on one and test on the other. But in terms of the robustness perspective, we can see that actually there could be some attackers. Say you can manipulate the testing time distribution such that the prediction during testing time is wrong, is misled. Therefore, this is so-called evasion attack, right? And similarly, the attacker can attack training time distribution. For example, for these types of Yelp or recommendation systems, you can create fake account, fake reviews to pollute the models, and therefore the model will have these types of training time attack. Usually it's called backdoors or poisoning attacks, right? And from another perspective, if we want to infer the distribution information of the training data, that lead to privacy problem, right? Usually we have like unified privacy attacks by like membership and model inversion attacks to infer the training data distribution or training data instance level information. And such inference can be used by peer queries or based on some prior knowledge to prop the trained machine learning model, right? Which is quite dangerous. And as well as the generalization problem, in addition to robustness and privacy, the generalization problem exactly is also dealing such a distribution drifting problem under the natural scenario. So here, both robustness and privacy is dealing the distribution drifting or distribution inference under the adversarial environment, right? And here it's under the natural environment. From day to day, our data will drift and will change a little bit, right? Will evolve. And how we can capture such distribution evolvedness and therefore learn a generalizable machine learning model. So you can see this have strong connection with such adversarial data distribution drift, right? And of course, these are three main components we may want to discuss in this talk. But of course, among them, there will also be different interconnections between them. For example, a simple example is that you can imagine if I have a perfectly generalizable model, right? Then there will not be robustness problem because under any distribution drifting, I will always be robust, right? Including such adversarial distribution drifting. But of course, that's almost impossible to learn a perfectly generalizable model. But still, the techniques in these two areas will be able to help enhance each other. That's what I want to say. And similarly for privacy, if the model is very private, so usually it means the model satisfies certain smoothness properties, and therefore it will also benefit the robustness as well. And we have some papers showing that given epsilon delta DP private model, you can achieve certain robustness as a function of the epsilon delta. So that's just some examples. So what I really want to say is that under this trustworthy machine learning, although I believe everyone have heard about it a lot of times, but mainly I think there are several components. For example, robustness, privacy, and generalization, and they also have like fundamental interconnections between them. So if we understand one and understand the connections, it will be largely benefit for the exploration or research on the other perspective, so that we don't need to reinvent the wheels and do like start from scratch again. So I think these connections between all of them would be very interesting, and that's mainly the main message I want to say about this talk. But next, I will explain one or two examples under each topic among these three, and give some flavors about, say, what we do in terms of robustness and what we do in terms of privacy and generalization. And then you can get better idea about why they are connected and how like research from one perspective could help another. So first, let's start from the robustness perspective. Right, so I believe a lot of you may have already seen such adversarial examples, meaning that given like 2D images and adding a small magnitude of perturbation, it can mislead the machine learning model to be classified as arbitrary adversarial target, which is called targeted attack. Right, and maybe some of you are also seeing the examples in real world cases, say like for some real world like road signs or pedestrians or things, if you add some stickers to the t-shirt of people's stickers to the t-shirt, or add some stickers to the road signs, the autonomous driving vehicles or just the cameras or different machine learning models, including LiDAR and cameras, could always be fooled. So here I will just give some example in case someone haven't seen such example, and then we'll go to mainly the defense part, which is the core component in the robustness part I want to say in this talk. So first of all, these are example in real world case that these types of stop signs can be easily like manipulated and attack the machine learning model. For example, in this static example, all the stop signs in this slides are misrecognized as a speed limit sign 45, which is very dangerous because your car will never stop at the stop sign. And the right turn sign will be misrecognized as a stop sign. And all the like different rows shows different types of perturbation. Different colors show different types of perturbation, and different rows show different like physical conditions. For example, the angles, distances are quite different. But we can see these types of physical perturbations are always resilient and effective against the different machine learning models. So that's quite dangerous, I would say. Right. And this is a static analysis and example. And here I want to show some dynamic evaluations, which means you will drive this car towards this. One is the adversarial manipulated road sign we showed before, and one is the vanilla road sign as a control experiment. And if we drive the car towards it, from the captions, you can see that on the left-hand side, it's always consistently misrecognized as speed limit sign 45, no matter what the physical condition is. And on the right-hand side, the control experiment is always stop sign. And similarly, this is another example, and you can see consistently on the left-hand side, it's misrecognized as a speed limit sign. And after this example, maybe some of you have seen and some of you haven't seen it. And then people ask a very interesting question, saying this is for classification models, right? So what about other models like object detection or different types like semantic segmentation, etc., etc. So this is one example for object detection. So very interesting, like still this stop sign example with a sticker on it. And here we use the FastRCN as the target model to attack. And you can see all the objects here can be correctly identified, right? Except this stop sign, unless you go to very, very close to this sign. and you may be able to recognize it because of the letters here, because we on purposely do not want to cover the letter. Otherwise, human cannot recognize it, right? The goal for these types of attack is that human cannot recognize it, so that human will not easily replace it, but machine learning model will be fooled, so that it is called stealthy. Right, and this is very interesting because first we show, okay, object detection can be attacked. And second, we show this is a white box attack, meaning that we have access to this fast RCN machine learning model. And next, we want to test whether this black box setting can be attacked as well. That means one famous and very interesting phenomenon called adversarial transferability, meaning that if you generate the set, like the perturbation against the model A, this perturbation have high probability to transfer to attack model B as well. Although this model A and B could be trained with different data, could be trained with different architectures and different initialization, etc., etc. So that's very interesting empirically, right? And of course, we also theoretically analyze the lower bound of and upper bound of such adversarial transferability and see exactly what's the factors that should affect such adversarial transferability. And the short answer is the model gradient closeness and the model smoothness affect a lot for such transferability. But for more details, if you are interested, we can direct you to our papers before. So this is the same adversarial perturbation we seen in the last slides, but we tested against the YOLO model, which is quite different model and in different environment. And we can see again here, the stop sign itself can never be recognized unless you get very close to it and it sees only recognize the letters, right? So this is very interesting and also very dangerous because black box models can be attacked, right? So what can we do about it? And this is a result that mentioned by Professor Liu that, yes, this road sign actually is exhibited in the Science Museum of London and people are playing with it. Again, shows that how trustworthy machine learning is important, interested to the broader community and the society. So beyond this, like a camera example attack, right? So people say, okay, you can attack classification and attack like object detection and the semantic transformation we can attack as well, just don't show here. And how about other sensors, right? Say in autonomous driving, I see in AIR we care a lot about the transportation autonomous driving, right? So I want to give a quick example about in autonomous driving, we have a lot of sensors, right? And sensor fusions like LiDAR, radar, camera, and fusions, etc. So can we also attack these types of LiDAR systems, for example, with 3D point clouds as input? So of course, the short answer is yes, right? I think you can guess it. But I want to quickly show some example to let you know how severe such attack could be, and we can go to the defense part. So this is just an overview about the LiDAR pipeline for the Apollo, Baidu Apollo autonomous driving system, which is open source. So here I want to show that the pipeline itself is very complicated, right? It's not an end-to-end differentiable machine learning model. It has different components and the non-differentiable components and connected, etc., etc. But even such a complicated pipeline, I would say can be easily attacked. And the attack methods will still be optimization. So we optimize the 3D point cloud by controlling the 3D, say, chamfer distance in the 3D space, such that the generated 3D object could be of relatively meaningful shape, which is stealthy to human, but will attack the LiDAR systems, for example. And as an example, I want to show that this is a real-world testing, actually in the highway in Beijing. And when the car drives towards it, the LiDAR systems will identify this is a box with similar size. This is optimized 3D object with 3D printed out, and we put it on the road and drive towards it. In this adversarial environment, you can see this LiDAR detection here never see anything. That means the car will actually drive into this obstacle if nothing is detected, right? And similarly, as the control experiment, we can see the LiDAR actually can identify this box quite accurately. And this is the green box showing that the LiDAR is detected this object. And another example is that we can put the object on different positions. And similarly, we can see that still the LiDAR cannot detect this object, which is dangerous. But for the control experiment, this box is always detected in this as this green one. So this shows that only the LiDAR point cloud systems and LiDAR sensors can be easily attacked, right? And without doubt and without any like a weird shape, this object is actually quite reasonable, at least to me as a human. Right. And after this example, people like actually there are many papers showing the advantage of sensor fusion. For example, sensor fusion can help improve robustness, generalization, etc., etc. And very interesting in the security community, people can see there is always this cat and mouse game, right? You have a new attack, you have a new defense, and you have a new attack again. And later on, we'll discuss how we can potentially end this repeated game, right? So here are some like many literature showing that sensor fusion would be helpful. Like sensor fusion would be the solution to like help improve the robustness, right? But let's see whether it's true or not. So basically, this looks like a complicated pipeline, but I want to just show it here so that you can see it's not that hard to generate an object that can attack both LiDAR and the camera at the same time, so that the sensor fusion system will be totally attacked as well. For example, for this core object here, we can optimize joint optimize the LiDAR 3D point clouds like a shape, as well as the surface of this object, such that the camera will be fooled. And then we joint optimize it and add some stealthiness like a 3D distance and 2D, say, like a TV loss for the texture smoothing, so that the texture and the shape will not look very weird. And then if we put such an optimized, adversarial object, which looks not that weird to me, right, compared with the benign, in the real world, like autonomous driving environment, we can see what can happen. So this is in the LG and Apollo simulation environment. The first one is the adversarial object. So if we put here, we can see the car actually never recognized this object even under this sensor fusion system, which means in real world, the car will run into it, which is quite dangerous. But in the control experiment, the car can easily see such object and stop at it. And so we definitely hope that we can develop some either testing or training algorithms to enhance the robustness so that the car can actually identify such a stealthy adversarial object in real world. And there are more like examples along this like object detection attack in real world examples. And if you're interested, you can take a look online. So overall, I would say that such like attacks have been explored and revealed to different autonomous driving companies, and people are using them for testing purpose and the robustness purpose, etc., etc. So I would say this is a very interesting topic and direction, and yeah, more robust algorithms and methods are definitely required before I think we can develop autonomous driving for every applications and scenarios. So far I would like hope I can convince you that the attack against the machine learning models are very easy, right? You can attack single models, you can attack ensemble models, you can attack one modality like sensors, you can attack sensor fusions. Like I always tell with my students that give me any machine learning model, right? It's always easy to attack it. I haven't seen any models that cannot be attacked yet. So later on, of course, as a white hat people and good people, we want to develop robust algorithms to enhance the robustness of the models, right? And therefore, there are a lot of defenses coming out since 14th and 17th, and now I think it's thousands of papers about defense and detection. But many of them, or most of them, are attacked again, as we mentioned before, due to this repeated game process, right? So therefore, we really need some theoretical guarantees for robustness, such that we can provide some certification for robustness rather than just test the empirical robustness or accuracy, right? Imagine that if you buy autonomous driving vehicle, I can tell you that, under the testing environment, I can collect that your accuracy is 90%. Like, do you dare to drive this car? I don't think so, right? Because you don't know what it will happen if it go to a new environment or a weird adversarial environment. So definitely I need to provide you something like, as long as the environment doesn't change this much, the accuracy will never be below than say 90% or something, right? With such guarantee, then you can say, okay, I'm more confident to use such a model because I can estimate how much my environment will change, and I will be aware of these types of large environment changes, right? So that lead to a whole bunch of, actually a new branch of research, which is certified robustness. And this direction, I would say, is relatively new. It's started 3 years or about 3 years before. But since it's very important, and along this line, now there have hundreds of thousands of papers and works to discuss different strategies for providing certification for machine learning robustness. And in a short summary, the certification means the lower bound of accuracy of machine learning model under certain conditions. And you can define such conditions, for example, in terms of LP bounded perturbation environment, or a certain semantic transformation bounded environment, etc., etc. But you hope you can give some lower bound for the accuracy so that you know what will happen to this model considering the worst case scenario, right? So that's a goal, or that's a philosophy to provide such certification for machine learning models. And this is a brief overview about this. We actually have one overview about this line of research, and briefly, it can be this types of method can be categorized into different branches. And if you are interested, you can take a more look at the paper, and there is a leaderboard with open source toolbox. You can implement all the algorithm here easily with this toolbox. And I think the thing I want to mention is that for the verification or certification, there are first two high-level branches, complete and incomplete. Complete means that you both certify the false positive and false negative, meaning that if I tell you this instance is not certifiable, it means it cannot be certified no matter what happens. But the incomplete certification means that if I tell you this instance cannot be certified, yes, it cannot be certified, but if this instance I tell you that this instance is certifiably robust, it will be 100% certifiably robust under this condition. But if I tell you this instance cannot be certified, it's not necessarily mean it's not robust. It could because it's not robust, and also could because my bound is too loose, or my method is too loose, so that I have no ability to certify it, which means you will be able to certify the false positive, but you will not give a complete certification for false negative. You could have some false negative, which is less dangerous, because if I tell you something is robust, then there's nothing wrong with that. If I tell you something is not robust, maybe among them, some of them are robust, you just miss them, which is kind of fine in terms of from the robustness perspective, right? So then with the complete certification, it's very expensive. That's why many research also turn to incomplete certification. So for complete certification, we need to solve a constraint optimization. Basically, you estimate the worst case perturbations, right, with different methods like branch and bound and different like LP and the integer linear program to solve the constraint optimization, which is very expensive, you can see. So far, this branch only can scale up to about 200 or 300 neurons, which is much fewer than the existing real world like machine learning models, right? And for the incomplete one, you actually can have a lot of flexibilities to do it. For incomplete, you can also divide it as deterministic and probabilistic. For deterministic, we have different relaxations from this branch to solve the constraint optimization. And for probabilistic, it's based on the smoothing technique, meaning that you smooth whatever machine learning model you have, such that you take the aggregation and such aggregation based on certain key lemma, for example, the Neyman-Pearson lemma, which is one of the key lemma. You can prove that with high probability, like 99 probability with enough samples, then your certification will be derived. So this is the overview of the certified robustness, but that's a large topic. I can spend one day talking about that. So I will give this high level like categorization, hope that it will make you easier when you read individual methods later on. And give some like state-of-art analysis about this line of research, right? So far on small data sets, for example, MNIST, the state-of-art certified robustness is about 93 under the L infinity radius 0.3. And the empirical robustness we can test so far is 96. So you can see this gap is not that large. So we can kind of say that on MNIST, we almost, achieve tight certified robustness, which is great. But when the data goes to slightly larger and more scalable, you can see on CFAR, so far the state-of-art certified robustness under this radius is 39, but we can see under the empirical robustness is 65. It's about twice. So it's relatively a large gap. So that means either we don't find enough, like adversarial enough attack or powerful enough attack yet to further lower down this number, or we haven't got good enough or tight enough certification method yet to further boost this number to be close with this one. To me, I believe the case is the second one. So I believe more like efficient and effective certification method can be developed such that this number can be further improved. And of course, if you give a large-scale data set like ImageNet, currently the certification is almost hopeless. It's 27%, and we know that currently on ImageNet, you can achieve very high empirical accuracy. So that means on large data set, there is a huge gap between certified robustness and binary accuracy. So I think this is a very interesting and promising line of research that people can focus on to develop new and effective algorithm to improve the certification bound of the robustness. So this is a state-of-art overview about the certified robustness and how to improve it. As we can see, there are many ways, like improve the architecture of the model, improve training strategies, improve data augmentation. For example, people show that if you use semi-supervised learning with unlabeled data or like adversarial data as data augmentation or different transformations, you can always improve such robustness a little bit. There are different ways, but in this talk, I want to focus on one way to give a little bit more detail about one philosophy I have about robustness, which is, can we leverage human logical inference or domain knowledge to improve the robustness and the certified robustness of machine learning models or machine learning pipelines? So what does that mean? Right? So this is a screenshot I captured this year from the NIPS challenge that this reinforcement learning achieves the best performance in this challenge because of the use of the tacit knowledge. So now people start to consider how we can embed or integrate domain knowledge that humans have to machine learning models, right? I bet many of you have heard such philosophy as well. So to me, I think incorporating small amount of domain knowledge or logical inference to machine learning model or pipeline will indeed dramatically help robustness and certified robustness as well, because you can see that all the attack examples we shown before, like the stop signs or the other attacks, to human, they are valid, right? They cannot attack human, but it can effectively attack machine learning model. Therefore, you definitely wonder whether you can leverage such human inference and logic analysis to improve the robustness of the machine learning model. So I will go to a little bit detail about this work, which is, I call it the sensing reasoning pipeline, which is one type of pipeline to integrate domain knowledge or logical inference. But I think there are many other ways to do it as well. I hope like my example here can inspire you to have different framework for it later on. So in terms of integrating domain knowledge, right? We definitely also want to leverage current statistical machine learning advantages. For example, effective like feature extraction and expressive network structure, etc., etc. That means we will not throw out neural networks, right? And we can integrate the neural networks as a sensing model, which takes the input and the output something, right? And we will connect a reasoning component after the sensing models. That means for each neural network, the output here, we call it an interface variable, and later on the factors will be the interval factor. So we take this input, and this logical inference reasoning component can be developed as, say, Markov logic networks or Bayesian networks, like different types of statistical graphical models, right? So the connections or the factors here embed the knowledge, right? So we'll give another example later on for details. So on the high level, you can see the input will be given to the neural network, and the neural network output will be given to a reasoning component. And the reasoning component has already integrated the knowledge, so that based on this pipeline, if say this neural network is attacked, right? And then this logical inference may identify these types of inconsistency of the output of these different neural networks compared with the domain knowledge, right? For example, we say a cat belongs to an animal, but if I attack this cat to output as a stop sign, then my logic will be a stop sign belongs to an animal. And of course, this is wrong, right? We know a stop sign doesn't belong to animal. Then this reasoning component will try to help correct the prediction again. So this is a high-level intuition. And I would say, or people may ask, yeah, whether it's possible to attack all the sensing models together such that it satisfies the logic here. I mean, that's very possible, but I would say that's very hard. That means you not only attack all the models, but also they need to be attacked such that the logical relationship still satisfies. So if the attacker can do that, I mean, yes, the attacker will attack it, and that's a very powerful attack. And in addition to this intuition about robustness, we also want to provide certification for this end-to-end robustness so that we can certify the lower bound of the accuracy of this machine learning pipeline. So give a more concrete example, we can see for developing this pipeline, there are several challenges. First of all, the graphical models, for example, MLN inference is Sharpie complete, which is very complex, right? We are not able to say do ImageNet 1000 classification with such a complicated inference time. But in the meantime, they also provide some opportunities. For example, these types of graphical models have nice exponential family, and they can provide such functional structures to solve the min-max that we want to solve in robustness. So concretely, we can see that in terms of building such a pipeline, it looks like this. So given the input, you can send the input to different sensors. Like this dog sensor classify whether the input is a dog, whether the input is a cat, whether the input is an animal. And all of them will be connected to this logical inference. And this inference shows that the knowledge is that, okay, the dog belongs to an animal and the cat belongs to an animal, and that's a corresponding factor, right? And that's what I said, that if this factor, or if this sensor is attacked into, say, stop sign, such a factor should realize that and recover that, right? And we learn different rules and learn different ways for the factors here. And therefore, we can derive this. So basically, by building up such an end-to-end sensing reasoning logical inference pipeline, we hope to get the like the lower bound of the accuracy, right? And let's look at what's the lower bound of the reasoning component here. So basically, given the MLN, you have all the probability predictions for the point here. And for every PI, which means every component sensors or factors here, you will have the assignment, right, with different possible word. And Z1 means the valid possible word, the number of valid possible word, divided by Z2, which means all the possible word, right? And you can see Z1 is calculated as this way, and Z2, which like sigma equals 1 means it's valid, and Z2 will be consider all the possible word. So basically, in this reasoning component, we want to get an upper lower bound for such Z1 divided by Z2, which is a marginal probability inference. So as long as we get this, we can bound the marginal prediction probability for this pipeline. So we know the lower bound of the accuracy of it, right? Of course, this problem is hard. So we know that there is a famous counting problem in math, and it is Shapi complete, and we can easily reduce the robustness problem into this counting problem, just like we prove any NP problem before. And therefore, we can prove that this robustness problem, which can be reduced from the counting, is also Shapi complete, and similarly for MLN hardness. So although given such a non-linear inference time complexity, we can make such additional assumptions to make such bound happen. So here I want to show one example, which is, as we discussed before, we want to calculate the marginal probability bound for Z1 divided by Z2, right? And if we take a log, it will be Z1 minus Z2 here, right? And here, of course, since Z1 and Z2, in terms of their inference time for MLN, is Shapi complete, therefore, we can make some assumption, which is we can assume that we have an oracle for the inference, right? And such an oracle can be formulated as the true inference plus the noise here, right? And this is the oracle that we have. And of course, we don't know the ground truth here, and it equals to the ground truth plus the noise here, and the noise is bounded. And based on such assumption, which is not very strong, I believe, but it gives very nice properties, which we can easily prove that this noise itself, you can view it as a perturbation magnitude, right? And such perturbation is bounded by C, which is a magnitude we want to bound. And we can prove that when this a variable like coefficient lambda is larger than 0, the R, which is Z1 minus Z2, is always monotonically increasing. And if it is smaller than -1, it always monotonically decreasing. So we will know that the upper lower bound of this whole value will be obtained at the 2 points minus C and C of the perturbation itself. And if the lambda is in between between -1 and 0, we can prove it convex, but it's not monotonic. So we can still use zero order gradient method to find the optimal, and the other one is achieved at the point still minus C and C, right? So with such analysis, you will be able to see that we can certify this, say, MLN logical inference component as well, and connected with the sensing model like the neural network certification, we can get this end-to-end certification. And similarly, such analysis can be derived from MLN to Bayesian network and etc. I will not go to detail about that. And then let's look at some examples. So here is an example of this primate net, meaning the goal is to classify all these like monkey types from ImageNet, but there are two types of knowledge we can leverage in such a scenario. One is the hierarchy edge, which means the great array belongs to array like that, right? And one type is exclusive edge, meaning if you are, say, great array, you should not be laser array anymore, right? You can only be one of that. So basically, with these types of first order logical representation, we can easily embed such logics into our, say, MLM model and train this end-to-end sensing reasoning pipeline. And when we look at the result, we can see in terms of binary accuracy with knowledge, which is this such sensing reasoning pipeline, and without knowledge is a single neural network, we can see that the binary accuracy doesn't drop and sometimes even increase a little bit. So that is very interesting because we all know that there is always a trade-off between robustness and binary accuracy, right? But we can see with such a knowledge integration, such a trade-off is relaxed. And not only your robustness will be improved, but also binary accuracy improve a little bit. And in terms of the robustness, we look at the robustness certification and compare with knowledge and without knowledge on the different smoothing parameters, which is smoothing for state-of-art robustness certification for neural network. We can see that with knowledge, the certified robustness and certification ratio is almost double, like twice, compared without knowledge, which is quite surprising and quite significant, right? And this is one example for such ImageNet types of image classification, and such a sensing reasoning pipeline can be easily adapted to different NLP tasks as well. For example, here, this NLP task is like the stock price prediction, and the input would be the news from crowd from Twitter and other places. And the knowledge we use is that, say, if your company make profits, your stock price should increase. And the second type of knowledge is that the increase of the price and the opening and closing price should add up, right? Like A plus B should be equals to C, like that. And the arithmetic rules. So basically, based on these two types of rules, and we can see that actually in this NLP task, the certified robustness also improve a lot, and also the binary accuracy doesn't drop at all. And in this figure, we want to show that not only the robustness improves, but also it improves with high confidence. So green means robust, purple means like pink means non-robust, and here the y-axis means frequency, meaning the higher the confidence is. So you can see the blue bar here with knowledge. It's not only always go to the green background, which means it's correct, but also very high confidence. So that's actually very good, meaning the model is very robust and stable. It's not easy to be attacked easily. So this is a very interesting example in terms of image and NLP tasks. Another quick example I want to show is come back to our previous example of stop sign, right? Because I want to show this example to let you know that indeed the stop sign example we showed before can be robustified, which means we can use a sensor model to predict whether it's a stop sign and use another to predict what's the shape of it and what's the color of it, or whether there is a letter like stop inside, etc. So the knowledge we will use is two directions. One is if you are a stop sign, right? Like you get S here, you always infer O, which is a prediction here, means if you are a stop sign, you should always be octagon shape, right? You cannot be other shape. On the other hand, if you have the letter stop inside your sign, you will always be stop sign, right? You cannot be others. So this is two directional knowledge. Slightly different with previous knowledge. We have seen the hierarchical knowledge. So here I just want to show you that there are different types of knowledge we can integrate. And I will escape some theoretical analysis. Still, similarly here, we can provide the lower bound of the accuracy and also prove that with such a pipeline, the accuracy will always be higher than without such a knowledge. And the key proof idea is that we can find the regime that all those, like this auxiliary sensors, which representing the knowledge, will contribute. So you can see as long as those sensors will contribute, you will always easily find that the robustness is higher because you have additional information, right? So you can actually prove that this pipeline will always be more accurate than a single neural network model, which we call main sensor here, like a single neural network model. And very interestingly, we want to show that similarly as before, benign accuracy with such a sensing reasoning model is always slightly higher, which is quite nice. And in terms of robustness, it's very surprising that the x-axis here, like the 40 something, actually show all the different types of attacks, and the y shows the robustness. So here it includes like LP bounded attack, physical attack, like common, corruption, like JPEG, frog, those attacks, etc., etc. Because this pipeline is attack agnostic, right? It's not like a robust, like adversarial training. You need to know the attack type. Therefore, this type is quite generic, and we can see easily for the benign accuracy, it's improved. And under physical attack, which is the first types of attack here, this knowledge pipeline increase like 70–80%, which is significantly high. And in terms of this infinity attack under both white box, black box, under different like unforcing attack, which include the fog, JPEG, elastic, or other different types, is if you look at the green here, right, not the numbers, just the green, you can see it improves all over the places. And under common corruptions, like contrast, brightness, is always increased. So here I will just, hopefully I can convince you or deliver one philosophy that the knowledge integration and the logical inference integration into machine learning pipeline can indeed improve the model robustness and the certified robustness. So I think that's a very promising direction. And not only for images, but also for like NLP task, we have this new like NIPS benchmark for all the NLP tasks. And for like reinforcement learning task, you can always improve the robustness by a large amount, and as well as provide theoretical guarantees for them. And this, so far, we talk about a lot of like logical knowledge, right? And there are some quick example I want to show is that you can also integrate other types of knowledge. Like here, we try to develop the autonomous driving testing scenario, which is safety critical, so that we can test the worst case scenario for autonomous driving. And we leverage the knowledge to help develop such like a generative model saying that the car should always on the road, it should not fly in the air, and the two cars should not over like lapped, and between cars there should be some distances. These types of basic common sense knowledge, after integration, the generation is much more efficient and effective. And similarly, another types of knowledge is causal relationship, right? So we know if there is a human want to cross, and we know given such causal relationship, we can leverage it to generate the scenarios by taking such causal relationship into account. So overall, I want to say that with all types of knowledge, causality, like a common sense, and like different first order hierarchy, usually it's helpful. And I think it's worth to explore all other different types of knowledge and further improve the resilience of the machine learning models. And a next example I want to show is that so far we talk a lot about testing time, right? We talk about testing time adversary, different attack. We talk about defense. We talk about certified defense. And we talk mainly about how to leverage logical and domain knowledge to improve the certified defense for machine learning models. And here I want to use just maybe 5 minutes to talk about training time attack and using the example of federated learning. Because for federated learning, regarding the testing time attack is similar, but during training time attack, it's very vulnerable and very realistic. Because in federated learning, right, you cannot control the individual agent. They are benign agent or adversary, right? You have many agents. So it's very possible, right? Some agent are adversarial, right? So that means in traditional federated learning framework, local users update the gradient to the server model, and then you aggregate and send back. So everything is perfect, right? However, if you have one, such adversarial agent which have these triggers to try to attack or pollute the model, then this trained model will be totally attacked, and severe consequence could happen. Therefore, we developed this framework, try to provide the first certification for robustness of federated learning against the training time attack. So on the high level, what we hope to obtain is that given such a perturbation, as long as this perturbation is bounded during training time for this attacker, we hope the trained global model still gives the same prediction for any test data before and after attack, right? Think about this. So even after attack, my model will make the same prediction with this model, which is never attacked before, given the same test set. Then that's a win, right? That's a certification. So that is the certification goal we want to achieve. So the way to achieve that is that, first of all, we need to clip and perturb the gradient when the server sends back to the local users, so that the gradient information, like the adversarial information in the gradient, will be kind of smoothed out slightly. And the second of all, the model itself on the server side need to be smoothed as well from the parameter smoothing. So I will not go to detail about parameter smoothing, but it's similar with data level smoothing with slightly different analysis for its certification of robustness. And with these types of strategies, like both aggregation and the server side parameter smoothing, it's actually possible to view the backdoor perturbation and the prediction consistency by looking at the model closeness, by viewing each iteration between local user and the server as the Markov kernel, and we analyze within this Markov kernel how robust the trained model is. D prime means the perturbed data and D means the vanilla data. We hope we know how close these two models are so that we can certify their prediction consistency, right? And there are many details I may not go to, but I want to show the result is that we can provide certification on different levels, like feature level, sample level, and the client level. And that means as long as the perturbation satisfies this value, this bound, and on the feature level, basically R here is the radius that for the backdoor or the perturbation during training time, and on the sample level you have different Q, and on the instance level you have client level you have different P. You bound everything such that intuitively you can see if you have larger radius or larger amount of adversarial agent, this bound would be smaller, meaning you can tolerate a smaller amount of perturbation in this process, right? So that means as long as my perturbation is smaller than this radius, the trained federated learning model will be consistent in terms of the prediction, which is a desired property. And here, let's look at some examples. So basically on different data sets like MNIST, EMNIST, and this long, which is a categorical data, and on the different smoothing parameters, because we need to smooth the server-side parameter smoothing, right? We can see the certified accuracy always is satisfactory until such certain radius. So you can see with larger radius, of course, the certification will be lower, which is a certified accuracy, right? So this shows that not only like a testing time, but also training time robustness, we can certify it. So far we have discussed all the things about robustness, and I think we may not have time to go to privacy since it's 1 hour talk. But on the high level, I would say there are many interesting privacy attacks and defenses as well. There are two types of privacy preserving machine learning models. One is generative model that you generate data in a privacy preserving way such that you can use this data for any downstream task. Another type is privacy preserving learning algorithm for specific learning types of models. And in terms of the generalization, we can calculate the model, like the data Shapley value in a efficient way so that you can provide generalization analysis and the data level understanding and explanation for the data level. Okay, so that is almost all I want to say. Yeah, so far we discuss mainly focus on the robustness side, and if you are interested in privacy and generalization side, we can discuss offline or during the question answer session as well. And in the high level, I really want to emphasize that these three components, including other like fairness and things, I think they are holistic framework, and they have fundamental connections from underlying. And if we like research them as a whole component from end to end, we actually can learn a lot and benefit a lot from one to the other. Okay. Yeah. Thank you, everyone. Let me know if you have any questions regarding it.